Welcome to this channel. Video gaming through Linux is possible. But if you wanted to play higher end video games without lag, you had to stay with Windows, no option. Back then, trying to run game inside a virtual machine on Linux was a nightmare. Games run extremely slow, visual look choppy, and controls lagged heavily. Because of this, most gamers had no choice but to restart their computers every single time they wanted to switch between work and gaming. I mean, if you are preferring Linux, however. I mean, however, tech fans refused to give up. They wanted the best of both the worlds. So, smart developers found a way to bypass these limits. They created a technology called GPU pass through. This allowed, however, a virtual machine to talk directly to your physical graphics card. Suddenly, the games inside a virtual system run almost as fast as they did on the regular Windows PC. And again, still there are new problem appeared. Modern anti-cheat system like FC 2026, 2027, and other titles started blocking virtual machine entirely, creating a huge obstacle for Linux gamers. But once again, the community stepped up to solve this issue. Today, those walls are finally coming down through a better software and constant updates. In this video, we will look into how developers overcome these massive hardware and software limitations, transforming Linux into a true powerhouse of gaming. So sit back and enjoy.
You spend thousands of dollars building a machine with top-tier components. The physical silicon is yours, but the moment you power it on, you realize you don't actually control how that hardware operates. For decades, accessing the full graphical processing power of a PC required paying a toll to a single proprietary operating system. Windows acted as the mandatory gatekeeper for high-end gaming and heavy workloads. If you wanted to use an open-source OS like Linux, you had two choices. You could partition your drive and constantly reboot to switch environments, or you could run traditional software emulation, bleeding massive amounts of performance just to get a program to launch. The software environment dictated the hardware's limits. The operating system acted as a warden, deciding which applications were allowed to touch the physical silicon. The open-source community, eventually backed by massive corporate funding from Valve, set out to bypass this restriction entirely. The objective was clear: allow code written exclusively for Microsoft's ecosystem to execute natively on Linux hardware with zero performance penalty. Achieving this required a systematic teardown of the software stack. Engineers had to start at the surface applications and dig all the way down to the bare metal. Removing these rigid dependencies strips the operating system of its gatekeeping power. It turns a locked proprietary environment into an open canvas where software runs wherever the user chooses. The first line of attack started in user space software. Developers utilized Wine and later Valve's gaming-focused fork called Proton to bridge the gap. These tools are not emulators. They don't simulate a fake Windows computer inside your machine. Instead, they act as real-time translators, catching instructions meant for Windows and instantly converting them into a language Linux understands. For graphics, a tool called DXVK intercepts Windows DirectX calls, translating them into the Vulkan API. This layer made tens of thousands of Windows titles playable, but modern software juggles dozens of threads: physics, audio, AI. When the matrix processes Windows synchronization commands, it chokes, causing the entire pipeline to stutter. Translating these commands in user space requires a constant back-and-forth round trip. As long as the translation sits on top of the host operating system, the CPU bottleneck remains. To fix the stutter, engineers had to dig deeper, past the surface applications, straight into the core of the Linux operating system. They developed NT-Sync, a specialized driver written directly into the Linux kernel to eliminate the round-trip translation overhead completely. Instead of translating Windows synchronization commands through a middleman, NT-Sync embeds the native logic for those specific Windows primitives straight into Linux's own DNA. The host operating system mutated its own architecture to natively process guest commands. By handling coordination directly at the kernel level, this rewrite yielded execution performance gains of up to 678%. Yet, even highly optimized kernel execution still relies on translation. For users who demand absolute, uncompromised performance, the final step goes straight to the physical silicon. It is possible to bypass the translation layer entirely and run Windows software exactly as it was designed, directly on the hardware. Through VFIO GPU pass-through, a secondary physical graphics card is isolated during the boot sequence. The host Linux system is forbidden from touching it. A Windows virtual machine is then mapped straight to that isolated hardware, taking unmitigated control of the graphics card on bare metal. This setup delivered flawless frame rates, but it created a massive hardware headache. Because the guest GPU was physically walled off, viewing its output required plugging a separate monitor and dedicated display cables directly into that second card. Relying on physical hardware switches and secondary screens defeated the purpose of a unified desktop. The software barrier had been destroyed, only to be replaced by a tangle of cables. The solution to this hardware bottleneck came from an open-source project known as Looking Glass. Looking Glass utilizes IVSHM, a virtual PCI device, to carve out a shared block of physical system RAM. Both the host Linux system and the Windows virtual machine are granted simultaneous access to this exact same memory space. The isolated graphics card drops rendered frames directly into that shared RAM. The host system reads the raw pixels straight from memory, bypassing encoding latency. The host and guest are no longer separated by hardware routing. By passing raw data seamlessly through a unified memory bank, the final physical boundary between the two operating systems is erased. From an engineering standpoint, executing Windows software on an alternative operating system is a solved problem. The translation pipelines, kernel optimizations, and memory sharing architectures are mature and highly stable. Modern processors are even integrating hardware-level memory synchronization, allowing legacy x86 applications to run natively on different architectures like ARM64 without heavy software emulation. Yet, thousands of major multiplayer titles remain locked out. Developers intentionally block access by deploying proprietary anti-cheat clients that require deep kernel-level privileges inside the Windows environment. These titles are perfectly capable of running flawlessly on Linux. The restriction is a deliberate corporate choice to reject alternative ecosystems, enforcing a software embargo disguised as a security measure. The massive commercial success of handheld devices like the Steam Deck has shifted the financial incentives. With millions of active players now utilizing Linux-based hardware, major publishers are quietly updating their anti-cheat parameters to capture that revenue. As these artificial blockades fall, users are no longer forced to choose between the software they need and the system architecture they prefer. The OS is finally decoupled from the silicon. When software executes fluidly across any environment, the machine you build is entirely yours to command.
If you have enjoyed the video, please give a like, subscribe, and we will meet again. Catch up soon. Peace out.